I want you to look around wherever you are right now. Like literally just look at the objects surrounding you, the device you're listening to this on, or, the mug holding your coffee, the clothes you're
It's
wearing.
the everyday stuff.
Yeah, exactly. And now I want you to try and imagine the sheer, just staggering scale of what it actually took to get those objects into your hands. Because there's a statistic that absolutely stopped me in my tracks when I read it. Over 80% of the world's merchandise trade moves by sea.
It's a massive number.
It is. And you might not think about global shipping on a daily basis, but it is this massive, kind of invisible, finely tuned machine, and it dictates the price of your coffee, the availability of your tech, and frankly, the security of your nation.
Yeah, and usually
Yeah.
when we think of international trade, there's this expectation of mechanical precision, right? Like
Yeah.
a ship leaves point A, arrives at point B, a crane moves a box, and a truck takes it away.
It's supposed to be clean.
Exactly. It's supposed to be perfectly clean and predictable. It's very comforting to think of it that way. We naturally want to imagine this perfectly choreographed global ballet where everything operates on a linear schedule. I
Yeah.
mean, the modern global economy was practically built on the assumption that ocean freight is cheap, reliable, and entirely invisible.
But then you dive into the actual data, and we have a really massive stack of sources today to do exactly that. We're looking at the UNCTAD 2025 Review of Maritime Transport, geopolitical analyses from War on the Rocks, industry white papers on port automation, and even these incredibly detailed academic studies on seafarer competencies.
It's a really diverse stack.
Right. And when you layer all of these sources together, that predictable machine looks like it is rattling apart at the seams. I mean, we are looking at a landscape that is incredibly turbulent.
It is the absolute definition of a perfect storm. We are seeing a complete upheaval in how goods move around the planet. And what's really striking here is that the pressure isn't just coming from one direction.
It's coming from everywhere.
Yeah, it's a simultaneous collision of geography, technology, climate, and human labor.
Which is exactly the mission of this deep dive today. Our goal is to unpack this collision of forces that is fundamentally reshaping global trade. We're talking about shifting geopolitical routes, mind-bending automation, a desperate, really high-stakes race for zero-emission fuels, and the human workforce caught right in the middle of it all. So, okay, let's unpack this, because the very map of global trade is being redrawn as we speak.
Literally redrawn, yeah.
And the data from UNCTAD gives us a stark mathematical picture of what that actually looks like. So according to the UNCTAD 2025 findings, global seaborne trade grew by 2.2% in 2024, but the actual distance those goods traveled, what the industry calls ton miles, jumped by nearly 6%.
And we really need to pause on that metric because the discrepancy between volume growth and distance growth is, well, it's the smoking gun of a supply chain in distress.
Because they're moving the same amount of stuff, just way further.
Exactly. The ton mile isn't just a measure of how much stuff is on the water. It's a measure of how hard the global fleet has to work to deliver it. When ton miles increase at nearly triple the rate of actual trade volume, it means ships are taking massive systemic detours.
Right, because of the geopolitical tensions in the Red Sea and the Strait of Hormuz, we're seeing major shipping lines effectively forced to abandon the Suez Canal.
Yeah, the risks are just too high.
So instead of cutting through the Mediterranean and the Red Sea to get to Asia, they're rerouting all the way around the Cape of Good Hope at the southern tip of Africa. And just to put the physical reality of that into perspective, you aren't just taking a slightly longer highway, you are adding thousands of nautical miles to a voyage.
Precisely. And the mechanical and economic impacts of that diversion are compounding. I mean, the Strait of Hormuz alone is a vital artery for the global oil trade. And the Red Sea is the primary conduit connecting Asian manufacturing to European consumer markets.
It's the main vein.
Right. So when you divert around the Cape of Good Hope, you are adding roughly 2 to 3 weeks of continuous transit time.
Which means the ship's massive engines are burning fuel for an extra 3 weeks.
Exactly. So immediately, your greenhouse gas emissions for that single voyage just skyrocket. But it also creates a massive vacuum in shipping capacity.
Because the ships are tied up on the water?
Yes. If a vessel is stuck sailing for an extra 3 weeks, it's missing its scheduled loading window back in Shanghai or Shenzhen. That ties up global shipping capacity, which artificially restricts supply, which inevitably spikes freight rates across the board.
And the UNCTAD report makes it very clear who absorbs the shockwaves of those freight rate spikes. And it's not necessarily the massive multinational corporations who have the capital to absorb the margins.
No, they just pass the cost along.
Right. The entities hit hardest are small island developing states, or SIDs in least developed countries.
What's fascinating here is how quickly a maritime disruption translates into an existential crisis for those specific economies.
Hmm.
I mean, for a small island developing state, the local port is a literal lifeline.
They don't have domestic manufacturing bases to fall back on.
Exactly. When freight costs surge because a container ship had to burn 3 extra weeks of fuel sailing around Africa, the shipping line doesn't absorb that cost. It is passed directly to the consumer.
And for net food importing nations, higher freight costs quickly and directly translate into more expensive imports. Like, it's a direct, inescapable line to food insecurity. The supply chain shock doesn't just mean your flat-screen TV is delayed. It means the price of basic grain goes beyond the purchasing power of the local population.
Which forces the global market to look for alternatives. If the traditional ocean routes are becoming this unpredictable, expensive, and frankly, politically fraught, the logical response from major economies is to simply bypass the ocean altogether where possible.
Which brings us to the massive counter-movement happening right now, which is nearshoring. U.S. companies are actively pulling their supply chains out of Asia and planting them directly south of the border. And the data here is just staggering. In 2025, Mexico saw a record $40.87 billion in foreign direct investment.
And that number isn't just speculative capital, it's hard infrastructure.
Yeah.
It is companies laying concrete, building factories, and establishing long-term logistics networks. It comes down to raw, unavoidable math.
Right. The transit times.
Yeah. If you are a manufacturer bringing goods from Asia to the United States, that ocean transit takes anywhere from 25 to 40 days. And that is assuming a perfect run.
Which we just established is rare.
Exactly. That assumes no choke points, no droughts lowering the water levels in the Panama Canal,
Yeah.
and no rerouting around Africa.
But if you manufacture in Mexico, a truck can move those same goods to a U.S. distribution center in 2 to 5 days. 2 to 5 days. That completely changes the fundamental philosophy of how a company handles its inventory. You no longer have to stockpile months of product in a warehouse.
Which ties up millions in capital.
Right, just a hedge against a ship getting delayed in the Red Sea.
Exactly. It drastically reduces the working capital tied up in static inventory. But there's another crucial layer driving this urgency, and it revolves around the upcoming 2026 USMCA review, the United States-Mexico-Canada Agreement.
And looking at this purely from the mechanics of supply chain strategy, regardless of the political dynamics, that 2026 review is functioning as a massive catalyst.
It absolutely is. The formal review process is expected to reset the rules of origin. In trade terms, rules of origin dictate how much of a product must be manufactured within the designated region to qualify for duty-free status.
Okay, so a certain percentage has to be actually made in North America?
Right. And if those limits on content coming from outside North America are tightened, well, companies want to ensure they already have the domestic infrastructure in place.
They want to be grandfathered in. So they are committing to Mexican production facilities right now to ensure they are positioned for whatever new tariff structures emerge. And you can see the physical footprint of this rush in the Mexican industrial real estate markets. Look at Monterrey, which is right there adjacent to Texas. It is an absolute powerhouse right now with an industrial vacancy rate sitting near an incredibly tight 5.4%.
And it isn't just Monterrey. Ciudad Juarez and Querétaro are seeing massive absorption rates for manufacturing space. We are seeing heavy investments specifically in aerospace components, automotive parts, and really complex electronics.
High-value stuff.
Exactly. These are industries that require highly integrated, extremely reliable supply chains, which is exactly what ocean transit is currently failing to provide.
But as massive as this nearshoring boom is, it's not a universal solution. You can't nearshore a rare earth mineral deposit. Some heavy bulk commodities, critical minerals, and specialized raw materials, they still have to cross oceans. So for the routes that absolutely cannot be nearshored, some major players are looking in a completely different direction to avoid the traditional choke points. They are looking north.
Up to the Arctic, the Northern Sea Route, or the NSR. As global temperatures rise and the Arctic ice profile changes, this route along the northern coast of Russia is opening up for longer periods of the year.
And the geographic math is undeniably tempting. I mean, if you take a standard cargo ship from Rotterdam in Europe to Yokohama in Japan via the traditional Suez Canal route, it takes about 22 days. If you go through the Northern Sea Route, it takes just 10 days. You are cutting the trip by more than half.
And if we connect this to the bigger picture, you can see why this is incredibly attractive to China. They've heavily integrated the NSR into their strategic planning. They openly refer to it as the Polar Silk Road. And this is driven by a very specific vulnerability known as the Malacca Dilemma.
Right, let's dive into the Malacca Dilemma because it perfectly illustrates why nations are willing to brave the Arctic. Currently, around 78% of China's hydrocarbon imports pass through the Strait of Malacca.
Which is a remarkably narrow, highly congested stretch of water between Indonesia and Malaysia. It is a strategic choke point. If that strait were ever blocked, whether by an accident, piracy, or geopolitical conflict, China's energy grid would face an immediate, catastrophic shortage.
Wow.
Yeah, so by developing the Arctic route, they fundamentally diversify their energy supply lines away from traditional, crowded, and potentially vulnerable corridors.
And we have actually seen proof of concept that the route is viable. The Christophe Marjorie, which is a highly specialized ice-breaking liquefied natural gas carrier, has made headlines making these record-setting runs. It delivered gas from the Russian Arctic to Asia nearly 30% faster than traditional routes.
True, but this is where we have to separate the theoretical appeal of the Northern Sea Route from the harsh, really unforgiving physical reality of operating in the high north.
It's not just a shortcut.
No, not at all. Yes, the distance is shorter. Yes, specialized vessels can make the run. But the indirect costs of operating in that environment are astronomical.
Let's actually walk through the mechanics of those costs, because I think there is a misconception that melting ice means the Arctic is suddenly just a cold, open ocean highway.
That is the furthest thing from the truth. First, you have the operational requirements. Even with receding ice, a typical cargo ship simply cannot safely navigate the route alone. They require icebreaker escorts. And those escorts are not cheap. Securing an icebreaker for a single passage in the winter-spring period can cost up to $1.4 million.
Wait, $1.4 million just for the escort?
Just for the escort. And then you have the insurance premiums.
Right, because of the risk.
Exactly. You are navigating an environment with notoriously poor satellite coverage, highly unpredictable extreme weather, and almost zero emergency response infrastructure. If a ship loses power or breaches a hull in the Red Sea, salvage tugs are relatively close. In the Arctic, you are entirely on your own, and underwriters price that risk accordingly.
And the ice itself behaves in ways that completely disrupt logistics. It isn't just one solid sheet that slowly and predictably melts, right?
No, the ice dynamics are incredibly volatile. As the younger, thinner first-year ice melts during the summer, it essentially unlocks massive, multi-year ice blocks. These are chunks of ice that have survived multiple melt seasons. They can be over 3 meters thick, they're as hard as concrete, and they float unpredictably right into the shipping lanes.
That sounds terrifying.
It is. Combine that with heavy summer fog that drops visibility to absolute zero, and your speed of advance just grinds to a halt.
This is exactly what I was thinking about when reading the War on the Rocks analysis. Wait, relying on the Arctic for just-in-time global shipping sounds like trying to choreograph a ballet on an unpredictable ice rink. Modern supply chains, especially the ones moving consumer electronics or automotive parts, require absolute precision, down to the hour. They book train and truck connections weeks in advance based on the ship's exact arrival time. If that is the standard, how can anyone rely on a route where a patch of summer fog or a rogue block of multi-year ice can stall a ship for 3 days?
They can't. It is a fundamental mismatch in operational philosophies. And that is exactly why the Northern Sea Route is fundamentally limited. The global container shipping industry, the massive vessels carrying the laptops, the sneakers, the medical supplies, operates on absolute schedule reliability.
Right. They can't afford a random 3-day delay.
Exactly. They simply cannot tolerate a multi-day delay due to a rogue ice flow. Therefore, the NSR will likely remain what analysts call a niche trade route.
Meaning it will be used primarily for point-to-point destination shipping. Taking raw materials extracted directly in the Arctic, like liquefied natural gas or iron ore, and bringing them to market, rather than serving as a replacement for the Suez Canal for general consumer cargo.
Precisely. It is a resource corridor, not a new global highway for containerized freight.
So we look at the board right now. The global trade machine is boxed in. Moving goods across the globe is becoming vastly more unpredictable and significantly more expensive due to geopolitics. The industry can't rely entirely on the Arctic because of the physical environment, and they can't nearshore every single product because of resource distribution.
Right, they're stuck.
Yeah. So when physical geography fails to provide efficiency, an industry in this much distress naturally turns to technology. And that brings us to the fourth industrial revolution, or 4IR at sea.
The fourth industrial revolution is generally defined as the blurring of boundaries between the physical, digital, and biological worlds. In the maritime context, it means fundamentally altering the physical reality of how ports operate and how ships are maintained through advanced digitalization.
Let's start with the ports, because this is where the bottleneck of global trade usually happens. We are seeing the rise of fully automated container terminals. After years of pilot phases and incremental upgrades, major hubs like the Port of Long Beach in the US, Shanghai in China, and Hamburg in Germany are bringing fully automated facilities online right now in 2025 and 2026.
And when we use the word automated, we aren't just talking about a remote-controlled crane. We're talking about a highly choreographed digital symphony. You have automated stacking cranes that arrange the thousands of steel containers with mathematical perfection. You have autonomous guided vehicles, or AGVs, zipping around the terminal tarmac, moving the boxes from the ship's side to the stacks without a human driver.
And what really blew my mind in the research is the brain behind all of this, the AI predictive analytics. The AI isn't just reacting to the boxes as they come off the ship. It is constantly calculating the most efficient way to load, unload, and store cargo based on when the truck is scheduled to pick it up, the weight of the container, and the physical balance of the stack.
It is optimizing the physical space in 4 dimensions. It's anticipating moves before they even happen, and the tangible result of that predictive optimization is staggering. The data shows that average gate-to-stack times, which is the critical metric of how long it takes for a truck to enter the port, drop off a container, and have it integrated into the stack, are dropping by 20%.
Wow. In an industry where a ship sitting at a berth costs tens of thousands of dollars a day, a 20% efficiency gain is a total game changer.
It absolutely is. It reduces human error. It allows for 247 continuous operation without shift changes or fatigue, and it directly mitigates the congestion that caused those massive supply chain backlogs we saw a few years ago.
Right, the pandemic-era bottlenecks.
Exactly. But the automation at the port is only one half of the 4IR equation. Because moving the box efficiently is great, but what happens when the massive machine moving the box breaks down? The other half of this revolution is happening in the manufacturing of the ship parts themselves.
Yes, and this was arguably the most fascinating part of our research stack. Let's talk about AML 3D and their wire additive manufacturing process, or WAM. To understand why this is a big deal, you have to look at the traditional repair model. For decades, if a massive cargo ship broke a highly specialized metal valve or a propeller component, they had to order a replacement.
And it wasn't a quick process.
No. That replacement had to be cast or machined in a specialized factory, likely halfway across the world, and then physically shipped across the ocean to whatever port the vessel was stranded in.
Which, as we just established, is a supply chain currently plagued by delays. Waiting 3 weeks for a part to be manufactured and shipped costs the shipping company hundreds of thousands of dollars in lost operational time.
But AML 3D has commercialized a process where ports and navies, including massive institutions like the U.S. Navy and BAE Systems, are 3D printing maritime-grade, large-scale metal parts locally, on demand, right there on the dock.
To truly appreciate why this is revolutionary, we have to look at the mechanics of the WAM process itself. Traditional metal 3D printing often relies on a powder bed fusion method. You have a bed of highly refined metal powder, and a laser melts it layer by layer.
Okay, makes sense.
The problem with that method is that it requires a highly controlled, enclosed build chamber to maintain the atmosphere. That physical chamber fundamentally limits the size of the part you can make. You just can't print a massive ship propeller inside a box.
Right, but AML 3D's wire additive manufacturing bypasses the box entirely. It adapts traditional arc welding technology. It uses a robotic arm equipped with an electric arc to melt certified welding wire feedstock.
Exactly. And the genius of it is how it protects the weld. Instead of putting the whole part in a vacuum chamber, the robotic arm uses a localized inner gas shield right at the print area to prevent oxidation as the metal melts. Because they are only shielding the exact point of printing, they are not bound by any size constraints.
So they can print huge stuff.
Yeah, a robotic arm on a track can print massive, free-form, dense metal parts. We're talking titanium. Or nickel, aluminum, bronze alloys known for high corrosion resistance in salt water right there in the port. Or theoretically directly aboard a ship.
And because it's additive manufacturing, the efficiency gains are incredible, right?
Oh, absolutely. It drastically cuts down on material waste. In traditional CNC machining, which is subtractive, you take a massive block of expensive metal and carve away everything that isn't the part. wasting a huge percentage of the raw material. Wham! Only deposits material exactly where the digital model dictates.
Here's where it gets really interesting, and I want to make sure I'm synthesizing this correctly. We're basically talking about downloading physical ship parts.
That's exactly what it is.
Instead of a ship waiting 3 weeks in a port for a custom titanium valve to physically cross an ocean on another ship, the port just receives a digital file. A giant robotic arm reads the file and prints the valve on the dock while the ship is unloading its cargo.
It sounds like pure science fiction, but it is happening right now in major dry docks. Decentralized manufacturing, which is exactly what WHAM allows, and centralized efficiency, which is what the AI automated ports provide, are really just two sides of the same fourth industrial revolution coin.
They are both mechanisms designed to bypass the physical vulnerability of the ocean.
Precisely. They are designed to insulate the supply chain from the exact geopolitical and geographic shocks we discussed in the first section. If you can print the part locally, you don't care if the Suez Canal is blocked.
It is a brilliant technological workaround. But as I look through our sources, I realize there is a massive, unavoidable elephant in the room. AI cranes and 3D printing solve efficiency and supply chain hurdles. They are amazing at moving cargo and fixing metal, but they do absolutely nothing to solve the maritime industry's most existential threat, the actual fuel that is powering these massive ocean-crossing leviathans.
And this brings us to what is arguably the most complex, expensive, and technically daunting challenge the industry has ever faced, which is decarbonization. To set the baseline, shipping currently accounts for roughly 2 to 3% of global greenhouse gas emissions.
That's huge.
It is. To put that in perspective, if the global shipping industry were a country, it would be the sixth largest emitter in the world, sitting right between Japan and Germany.
And the era of free-flowing emissions is over. The regulatory hammer is coming down hard. The International Maritime Organization, the IMO, has a net zero framework that is slated for formal adoption in October 2025. We are talking about implementing a stringent global fuel standard and a legally binding carbon pricing mechanism.
Meaning it's going to cost real money to emit carbon.
Right. Shipping companies are going to be financially penalized. The math is simple. If you burn heavy fuel oil, you pay massive taxes, so they have to buy new ships. Let's look at the 2025 Alternative Fuel Order Book for new vessels, because it perfectly illustrates the chaos of this transition. There are 1,942 ships ordered. 12,259 are set to run on liquefied natural gas, or LNG. 385 are ordered for methanol, and 45 are ordered for ammonia.
What you are seeing in that order book is the entire global industry grappling with the S-curve of technological adoption.
Break down how the S-curve applies here, because we aren't talking about adopting a new smartphone. We're talking about re-engineering global logistics.
Right. In technological adoption, the S-curve tracks a technology's maturity over time. Right now, alternative scalable maritime fuels are at the very bottom tail of that the emergence phase. The slope is practically flat because the technology is still fighting the infrastructure. We are moving toward initial scale, but we haven't reached maturity where adoption skyrockets.
It's still early days.
Very early. And the industry is currently split between the two leading candidates for scalable zero-emission fuels, or SCEF, ammonia, and methanol. Both have distinct revolutionary advantages, and both have terrifying physical drawbacks.
Let's dive deep into the chemistry and mechanics of both, starting with ammonia. The big undeniable pro for ammonia is that the molecule itself, NH3, contains zero carbon. When you burn it in an internal combustion engine, you get a massive 90 to 95% reduction in tank-to-wake carbon emissions. That is the dream scenario for hitting net zero.
It sounds perfect on paper.
But the cons. Ammonia is highly toxic.
It is lethally toxic. If there is a leak, it presents an immediate, deadly safety risk to the crew. It also presents a devastating risk to the marine environment if it spills into the water. Because of its properties, it requires significant, highly engineered redesigns of the ships just to store it safely. It must be kept pressurized or cryogenically cooled to remain in a liquid state.
And even though the molecule itself doesn't contain carbon, the actual process of burning it in a massive ship engine isn't entirely clean.
This is where the combustion physics become a massive hurdle. Burning ammonia carries the risk of what engineers call ammonia slip.
That doesn't sound good.
It's exactly what it sounds like. Unburned toxic ammonia escaping directly into the atmosphere through the exhaust. But even worse is the risk of generating nitrous oxide, or N2O, during combustion.
And N2O is a severely problematic gas.
It is a greenhouse gas that is 273 times more potent in its warming potential than carbon dioxide over a 100-year time frame.
Wait, 273 times.
Yeah, the combustion temperatures have to be managed perfectly. If your engine isn't perfectly tuned to mitigate that N2O formation, you might actually be doing more harm to the climate than if you were just burning traditional, dirty, heavy fuel oil.
Okay, so ammonia is a highly toxic, cryogenically stored alternative that requires perfect combustion to avoid catastrophic warming effects. I can definitely see why there are only 45 orders for it. Let's look at the other major contender, methanol. Now, chemically, methanol is much easier to handle. It's a liquid at ambient room temperature, which means shipbuilders don't need to install those crazy, expensive cryogenic tanks. But it is highly flammable, and it isn't just regular flammable. It burns with a completely invisible flame in the daytime.
Which is an absolute nightmare scenario for a ship's damage control crew. Imagine trying to fight a fire you literally cannot see on a ship in the middle of the ocean. Furthermore, unlike ammonia, methanol does contain carbon, so when you burn it in the engine, CO2 absolutely comes out the smokestack.
Wait, I want to make sure I understand the logic here. If burning methanol emits CO2, how does it qualify as a pathway to reaching net zero?
It only works mathematically if the fuel is specifically green methanol. This means the methanol is synthesized onshore using renewable hydrogen and sustainably captured carbon, perhaps carbon pulled directly from the atmosphere or captured from an industrial smokestack. So the carbon you emit when burning it at sea is simply returning the exact same carbon you captured to make it, resulting in a net zero life cycle.
Oh, I see. It's a closed carbon loop.
Exactly. But sourcing enough genuinely green methanol to power the global fleet is currently a massive supply chain bottleneck. The production facilities simply do not exist at the scale required.
And there is another physical reality that both methanol and ammonia share, which directly impacts the business model of shipping. Both of these fuels are significantly less energy dense than traditional heavy fuel oil.
Meaning you get less energy per cubic meter of fuel.
Right. So to travel the same distance, ships need much larger fuel tanks. The data shows methanol requires bunkering, which is the maritime term for refueling, twice as often as a traditional ship. Ammonia requires even more physical space to achieve the same range.
Which creates a brutal economic trade-off. If you are dedicating more of your ship's internal volume to massive fuel tanks, you are inherently carrying less cargo. Carrying less cargo impacts your profitability per voyage. It is a series of incredibly difficult engineering and financial trade-offs.
Okay, but let's look at the numbers again, because there is a glaring contradiction in the order book. We talked about the S-curve and these zero-emission fuels, but LNG, liquefied natural gas, has 1,259 orders. That completely dwarfs methanol's 385 and ammonia's 45 combined. But LNG is a fossil fuel. It absolutely still emits carbon. And worse, the sources explicitly mention the risk of methane slip, where unburned methane escapes the engine. And methane is 80 times stronger than CO2 and its warming potential over a 20-year period. So what does this all mean for you as a listener? What does it mean when you extrapolate the data? Are we basically slapping a massive, expensive Band-Aid on the climate crisis by using LNG as a bridge fuel?
It is a highly debated, incredibly polarized topic within the industry. Many analysts and shipping giants view LNG as exactly that, a necessary pragmatic bridge. They argue that a 20% reduction in carbon today using LNG is better than waiting a decade for the perfect solution. Because the reality is, the infrastructure for green methanol and ammonia just isn't there yet.
There's nowhere to buy it.
Right. The Maritime Decarbonization Hub has identified a massive financing gap. We are talking about trillions of dollars needed globally to build the green fuel production facilities and the specialized port bunkering infrastructure. The shipping companies are buying LNG ships right now because they know they can actually source the fuel today.
They have to replace their aging fleets, and they can't buy a ship that they can't refuel.
What's fascinating here is how the industry is employing mechanical, almost retrotech stopgaps to buy time and reduce emissions right now while they wait for these exotic fuels to mature. They are aggressively retrofitting existing ships with energy-saving devices, or ESDs.
I loved this part of the research. We are talking about physical modifications to the hull, things like rudder bulbs. And it's not just a fancy piece of metal, it actively alters the hydrodynamics of the ship. Behind a massive spinning propeller, you get these chaotic rake vortices, basically swirling energy in the water that creates drag. A rudder bulb sits right behind the propeller hub and physically smooths out that vortex, recovering that kinetic energy and translating it into forward thrust. And just that one piece of metal yields a 3.5% fuel savings.
And 3.5% on a ship burning 50 tons of fuel a day? is a massive financial and environmental saving over a year. But even more impressively, we are seeing a return to the oldest maritime technology in the world.
Wind,
We
yes.
are seeing the installation of wind-assisted propulsion systems, or WAPs.
Like the Brands Hatch, which is a new-build Aframax tanker equipped with these massive modern sails. They don't look like pirate ship sails. They look like giant spinning metal cylinders utilizing the Magnus effect, or rigid airplane wings standing upright on the deck. And the telemetry data shows they are yielding 5 to 15% fuel savings. It's incredible to think that in the era of AI and 3D printing, we are literally putting sails back on cargo ships to save money on carbon taxes.
It highlights the sheer desperation and the practical ingenuity of the transition. Every single percent of fuel saved is a direct reduction in emissions and a tangible cost saving against future carbon pricing.
So let's take a step back and look at the ship of the very near future. We have highly complex vessels running on either highly toxic cryo-cooled ammonia, invisibly flammable methanol, or methane-leaking LNG. They are being routed through politically tense, dangerous waters or unpredictable Arctic ice flows. They are navigating into fully automated AI-driven ports carrying 3D-printed replacement parts. Which brings me to what I think is the most important, often overlooked question of this entire deep dive. Who is actually managing all of this on the ground, or rather, on the water?
You are talking about the human element, the seafarers. And this is perhaps the most critical and currently the most vulnerable link in the entire supply chain.
Exactly. We can design a ship that perfectly calculates the hydrodynamics of its own rudder bulb while burning zero-carbon ammonia, but a human being still has to turn the wrench and monitor the screens. Let's look at the Filipino maritime professional study we have in the stack. The Philippines is the absolute backbone of the global maritime workforce. They provide over 385,000 seafarers to the global fleet. A recent academic study used a statistical tool called the Kruskal-Wallis H-test to evaluate their specific competencies in the face of this fourth industrial revolution.
I'm glad you brought up the methodology because the Kruskal-Wallis H-test is crucial here. It isn't just taking a simple average. It is a non-parametric method that lets researchers take ordinal data like a seafarer, rating their AI proficiency on a scale of 1 to 5, and determine if there are statistically significant differences across independent groups, like comparing different ranks or different age brackets against their technological skills.
Right. It gives a highly accurate picture of where the skill gaps actually live. And the findings are a massive wake-up call for the industry. The study found that these seafarers possess strong, above-average competencies when it comes to regulatory compliance and general adaptability. They know how to follow strict maritime rules, and they know how to survive the psychological toll of being at sea.
They're tough, experienced workers.
But when tested on the very technologies driving the 4IR digitalization, data analytics, artificial intelligence, and virtual or augmented reality, their skills are lagging significantly, sitting at average or lower proficiency.
And we have to map those skill gaps against the demographic realities of this workforce. It is highly male-dominated, and the largest concentration of workers is currently in the 41 to 50 age bracket. We have an aging workforce that has spent decades mastering traditional diesel mechanics, celestial navigation, and analog systems, and suddenly the technological ground is completely shifting beneath their feet.
Let's relate this back to everything we just discussed. Let's look at the cognitive load being placed on these people. An engineer on a ship in 2026 isn't just turning a wrench on a traditional two-stroke diesel engine. We are asking them to manage complex AI navigation systems that have to handshake directly with automated port mainframes. We are asking them to maintain complex cryogenic tanks and prevent deadly ammonia leaks. We are expecting them to manage the ship's digital single window.
Which is a massive vulnerability in itself.
Right. Explain the digital single window, because that drastically changes the ship's attack surface.
Traditionally, clearing a ship into port involved the master carrying briefcases of paper manifests to 12 different local authorities. The digital single window mandates that everything, cargo data, crew passports, emissions logs, is uploaded into one centralized networked portal. But because it is networked to the shore, it becomes a massive attack surface for ransomware or state-sponsored cyber attacks.
So we are asking a traditional mechanic to suddenly become a cybersecurity expert defending that portal, a chemical engineer managing toxic fuels, and an AI data analyst perfectly logging carbon emissions to comply with international tax frameworks all at once. If these men and women are stuck on ships for months at a time, often diverted on longer routes around Africa because of geopolitical tensions, exhausted and isolated, when are they supposed to learn all this?
This raises an important question, and it is a concept gaining significant urgent traction at the UN and the IMO, the absolute necessity of a just transition. The core argument here is that we cannot successfully decarbonize and digitize the global supply chain on the backs of an unsupported, undertrained workforce.
I saw the UNCTAD report specifically highlights this framework.
It does. A just transition means ensuring that the move to a zero-carbon, highly digitized maritime industry empowers workers rather than abandoning them or making their jobs impossibly dangerous. The UNCTAD report focuses heavily on physical and legal protections, protecting seafarers from abandonment, which is a very real risk when shipping companies go bankrupt or face sudden international sanctions and just leave the crew stranded in a foreign port.
The report also points out the desperate need for gender inclusiveness as a solution to the upcoming labor shortage. It notes that while women now hold nearly 40% of managerial and administrative roles in shore-based ports, they completely lack operational representation on the water and in technical roles. There is a massive untapped talent pool there, especially as 4IR automation changes the physical requirements of some traditionally labor-intensive jobs.
And crucially, it comes down to funding the transition. The IMO's Net Zero Fund, the billions of dollars expected to be raised from that upcoming carbon pricing mechanism we discussed, is proposed to be used not just for building new green fuel plants, but to systematically support comprehensive training and upskilling programs, particularly in developing countries. We have to fundamentally reskill the 385,000 Filipino seafarers and hundreds of thousands of others globally so they can safely operate these floating chemical plants and AI hubs.
Because if we don't, the technology won't matter. The shortage of qualified, confident seafarers will bring global trade to a grinding halt long before the Arctic ice melts or the Mexican nearshoring factories are fully built.
Exactly. The human element is the ultimate single point of failure in this entire perfect storm.
It is a staggering web of interconnected challenges. Let's briefly recap this incredible transformation happening right under the surface of the global economy because we have covered massive ground today. We started with the sheer scale of seaborne trade, which is currently being fractured by geopolitical tension, forcing ships to burn millions of dollars in extra fuel sailing thousands of miles around Africa, spiking food prices in developing nations.
And we saw how that geographic pressure is driving a massive nearshoring boom, pulling billions of dollars of foreign direct investment into Mexican industrial hubs like Monterrey to shrink supply lines from an unpredictable 40 days down to a reliable 4 days.
We examine the Arctic wildcard, where receding multi-year ice is tempting nations like China to pioneer the northern sea route to bypass the Malacca dilemma, balancing the promise of a 10-day shortcut against the brutal financial realities of $1.4 million icebreaker escorts and zero schedule reliability.
We looked at the industry's technological Hail Mary, the fourth industrial revolution. Ports in Long Beach and Shanghai handing the logistical keys over to AI and autonomous guided vehicles to shave 20% off gate-to-stack times.
And the mind-bending reality of wire additive manufacturing, where dry docks are quite literally downloading files and using robotic arcs to 3D print massive titanium parts on demand, severing their reliance on fragile global supply chains.
Then we confronted the trillion-dollar green fuel dilemma. The realization that the industry must abandon the heavy fuel oil was built on, forcing a choice between highly toxic zero-carbon ammonia, invisible flame green methanol, or relying on methane-leaking LNG as a bridge.
All while bolting high-tech aerodynamic sails onto decks to save every drop of fuel possible. And finally, we brought it back to the human beings. The aging, incredibly stressed workforce of seafarers being asked to transform from traditional mariners into digital, chemical, and cyber experts while stranded at sea, and the desperate need for a just transition to support them. So the next time you click buy and order a product online, take a second. Picture the geopolitical ballet happening out on the oceans. Picture the toxic fuel management, the AI cranes calculating the stack, and the Filipino seafarers working around the clock to get that cardboard box to your front door.
It is a genuine miracle that the system works as well as it does, and it is going to take a monumental, coordinated global effort combining engineering, policy, and labor support to ensure it keeps working through this transition.
We've talked extensively today about AI taking over ports and ships requiring advanced cybersecurity to protect their digital single windows. But consider this. As we push toward fully autonomous, uncrewed cargo ships in a desperate bid to cut costs and solve the looming seafarer shortage. Wait, what happens when a floating AI-driven tank carrying thousands of tons of highly toxic, cryogenically cooled ammonia gets hacked while navigating the environmentally fragile, newly melted, unpredictable waters of the Arctic? We are obsessing over upgrading the hardware of global trade, but we might be overlooking the ultimate vulnerabilities of the software running it. It's a brave new world on the high seas, something to chew on.